So good morning, good afternoon, good evening, everybody, wherever you might be. It is my great pleasure to welcome you to our seminar. Our today's speaker is from Texas, who is actually in the Boston area right now, GUOLIANG Yu. He will speak about quantitative K-theory, K-homology, and applications. So the Zoom is all yours. Take it away. You have full 90 minutes, but we will do our best to interrupt you with questions. Go ahead, Will.
Well, thank you very much. I would like to first thank the organizers, especially Peter, for inviting me. Okay, so I will explain the basic idea of so-called quantitative K-theory, K-homology, and some of the applications. So, okay, so I will start with quantitative K-theory. And in order to define or make sense out of quantitative K-theory, I need a geometric structure on the system algebra. So it's something very basic. It's just a length function, okay? And so it takes values in non-negative reals and possibly infinity. So I allow infinity, okay? So if A is a unitole, I want the length of the identity to be 0. And just for simplicity, I also want the length of the adjoint is equal to the length of this element. So I have those natural kind of inequality for a length function. And I don't want, I want the length function to be non-degenerate. So this is what the last condition is about. So the elements whose length is finite should be dense in the system algebra. Okay. Now, alternatively, if we consider the subset, oh, sorry, I'm missing an R, of elements whose length is less than or equal to R, and this gives us a so-called filtration of the system algebra. So these two concepts, length function and filtration, they are actually equivalent to each other. So, okay, now, so this is, of course, an extra structure on a system algebra, but it's actually kind of generic in the sense that you can always build length function like this. But let me give you some natural examples. Let's see. The first natural example is actually that's what motivates this construction. It's the group system algebra. So in that case, this is the concept of geometric system algebra is very much motivated by the concept of geometric groups. So just if you have a discrete group, and you can always put some natural length function on this. If it's finitely generated, you can have a word length, and if it's a countable discrete group, then there's always a so-called proper length function, and they are, for proper length functions, they are all kind of equivalent in some way. So this geometric structure, in some sense, it's intrinsic. You can have many different length functions, but they are all kind of equivalent to each other. Okay, now if we come back to a group system algebra, we can just use the length function on the group to define a length function on first the finite sum linear combination in the group algebra. Then if you have infinitely many non-zero coefficients, then we define it to be infinite. Okay, so of course we can generalize this concept to any cross product. Okay, and using this way, and so that's also quite natural. So okay, so now those are, of course, those are kind of system algebras coming from geometry in some way, but what if you have just a general system algebra? if you have a general cyst algebra, you can always also put like some kind of length function. For example, you can choose a generating set in the sense every element in the cyst algebra can be approximated by like product linear combination of element in this E. Okay. Now, if you let it multiply like n number of times, and it gives you a filtration. This. Okay. Now, whenever you have a filtration, you can define a length function. So you, in particular, it's quite interesting if we have a finitely generated cyst algebra. So we can choose like a finite generating set to create a length function. Now, two different finite generating set, of course, would give you a different length function, but asymptotically, they are equivalent. One can introduce a concept of asymptotic equivalence, actually for K-series purpose, and that's good enough. So it is, again, in the finitely generated case, this length function or this geometric structure is unique up to some like asymptotic equivalence. So it's quite intrinsic. And of course, you might say, I'm interested only in infinitely generated cyst algebra, but there are inductive limits of finitely generated ones. So in a way, if you understand all finitely generated cyst algebra, of course, you understand everything. Okay, so, sorry. So this is, so what I'm trying to say is that, a geometric structure or length function on a cyst algebra, it's a very natural and phenomena. So, okay, so now I'm going to like define so-called quantitative K-series. It's very elementary. It's very elementary. So I, in a way, I want to like restrict myself to K-series element in some scale, like controlled by the length. Okay. Now, and the only thing is, if we want to do this, we cannot restrict ourselves to projection or idempotent. We have to be a little bit more flexible. So the only flexibility is, instead of considering projection or idempotent, well, we can require it to be self-adjoint. I'm going to ask only for like so-called quasi-projection. It's almost a projection, but we all know when you have an almost projection, you can construct like a projection using a functional calculus. So it's not much of a restriction, and the only thing is that I want to put on now here. I want the elements to live like to have length at most R. So it's controlled in some scale. Okay. Now everything else, then you can define like a K group. In this way, just using this kind of elements. Okay. So this is not, at first glance, it's not much of an idea. And so why are we interested in doing this? Or maybe first we can also define similarly, like in the case of K1. So again, it's not possible if I restrict myself to like length R to have a lot of unitary. So we restrict ourselves to like only quasi-unitary. Okay, and that's motivated by geometric situation. Okay, so this way you define some kind of quantitative K groups, and okay, so now you might ask, why are we interested in this? So at the first glance, it looks like we are making life more complicated. Okay, so historically, this was like because like some older work of mine, like for the Novikov conjecture for groups with finite asymptotic dimensions. And in this general setting, it's my joint work with V. Okay, so let me explain why are we interested in this. And well, first of all, we observe if we let this scale R go into infinity, then we just recover the usual case here. Okay, so this is quite easy to see. And so it's a more like a refined K group. And secondly, that's the main reason. Actually, this like more like complicated quantitative group is more computable. Okay. And so we can develop like algorithm to compute quantitative K group. So the main reason this is more computable is that this kind of group, it's easy to do like cutting and pasting. Okay. Now for the usual K group, in order to do cutting and pasting in the sense of algebraic topology, you would have to use like exact sequences. Now, in order to use exact sequences, you would need like ideals. I mean, the concept of subspace, right? Now, generically, a lot of times it's, system algebras are kind of simple. They are simple in the sense they don't have ideals. So the basic technique from algebraic topology cutting and pasting don't work so well. And because when you don't have ideals, you cannot do cutting and pasting. Of course, you can use like more sophisticated like technology like KK and cyclic homology like to compute this, but at a more basic level. And so we have some technical issue. But for quantitative K theory, and we don't need ideals to do cutting and pasting. We only need like some like ideal in a very asymptotic sense. Okay, so I will try to explain this idea from a very easy example. Okay.
Sorry, Guoliang, may I ask you a very simple question? Could you? Oh,
yeah.
Yes. I'm looking at this limit. So you take it all with R going to infinity and you disregard the epsilon because you have this theorem that any self-adjoint element sufficiently close to a projection can be actually given. I mean, there is a projection which can represent the K0 class, right?
Yeah, that's a good point. So, I mean, actually, I choose one epsilon like this, but you might ask, why? So actually, for any, you can choose a different epsilon, and they are asymptotically, they are all equivalent to each other. But if you choose a smaller epsilon, you might make the R bigger.
Yeah.
So these two constants are kind of like balanced against each other.
Yeah.
But for this talk, I will fix one epsilon for, let's not pay attention to the epsilon anymore. So we can fix that.
Yeah, I could feel the balance. That was clear to me. But here we take the limit. So you are just getting rid of one variable. And then the question is somehow the value of epsilon important or not? It seems it's not because
it's convenient. Epsilon is convenient, but if we wish, we can ignore it. You can by making R bigger, you can always make your epsilon to be as small as you want.
Yeah.
So that's not really a problem. Yeah. But it's convenient to have the epsilon. Yeah. But that's a good point. Yeah. Thank you.
Excuse me, and also it does not depend from the choice of the length function, yes?
Oh, this group, actually, in the finitely generated case, this group still, I mean, in general, it still depends on length function. But in the finitely generated case, if you choose a different length function, there are relations between the constant. They are like asymptotically equivalent, but not for the same, exactly the same constant.
Okay, but after taking a limit, you get rid of the choice of the...
After, exactly. After you take a limit, you get the usual case here.
Okay, thank you.
Yeah.
Can I ask also?
Yeah.
Hi, it's Ludwig. I wanted to ask you from a mathematical physicist perspective. So if these C-star algebras are represented on a Hilbert space, what does it mean, this length function in the language of Hilbert spaces? Dimensionality on which these operators, is there any meaning?
It's not like, well, maybe we look at in the group case, right?
Okay.
In the let's see, in the group C-star algebra case, now you are acting on the helps L2 of G, so you are translating like the basis element, right? Each group element. So this length is like how much distance you are translating.
Okay.
Okay. It's sometimes we call it propagation. It's like the waves. You know how much it's propagating.
Okay.
Yeah.
Well, in fact, there is a, even in the group C-star algebra case, there is a hidden spectral triple behind, because you can look at the length function as an operator in L2 of G, and then this thing measures the size of the commutator with this, because it's a translation. So
that's an excellent point. So this is one can use Allen's like spectral like viewpoint to look at this. Yeah,
definitely there's Dirac operator associated to length function. I remember this work.
So this can be like this what I'm talking about could be like put into Allen's like non-commutative geometry using spectral triple concept in a very nice way. Okay, so now let me just show you why this how to like apply this idea to compute, for example, the cross product. Now this is like L infinity of Z, like with the group Z just translating on the Z. Now, of course, this is a relatively simple example. You can use some other method to compute the K group, but I want to just illustrate how you do like the computation of this using those ideas. So this idea, let me draw a picture. So I'm going to like, let me draw the picture of Z in a continuous way so it's visible, right? Okay, so we are trying to compute like quantitative K group at the scale R, but now I'm going to cut this Z into interval of equal length. So the way I'm choosing, like each interval is like somehow 10 to the 10. Well, this particular number is not important. Something much bigger than R, so of equal length. Okay, I'm just going to cut the little numbers like this. Now I choose x0 to be like, well, I guess I label them maybe, well, like 0, 1 to -1. X0 to be maybe the even number, the one, x1 to be the odd number, the interval, the union, okay? All right. So, and so I look at those like elements which are supported in x0 or x1, okay? And this entire thing, the entire C-star algebra can be written as a sum of elements either supported x0 or supported in x1, essentially. And neither of them is an idea of the entire thing. But on the other hand, for this K group, there is a Mann-Vittori sequence asymptotically, and we can compute the whole thing by looking at the K group, this kind of quantitative K group supported either on x0, x1, and their intersection. Okay. Now, what is good about? Let me color it. Maybe x0 is like the one, the even number one, and so the point is that between those even numbered ones, the distance is pretty big. And here I can only travel R distance, which means I cannot travel from one to the next one. to the next yellow one. It's like I'm living on this yellow island. You are living on this, you are living on the next yellow island. We are too far to talk to each other. So it's kind of, it just means like my son cannot get married with your daughter. Well, that's kind of tragic. And but for K-series, that's good. That's good because so you're isolated. So your operators are only supported on the yellow things, but on the yellow things, it's just compact operators. Okay, so this is the idea. So, but this idea, I mean, this is a very naive idea, and this naive idea works actually quite efficiently. For example, yeah, so we have, well, I guess this is the migratory sequence I'm talking about. Okay, but this idea works quite efficiently. And another interesting thing, for example, you can also make this works like cross product with Z, like irrational rotation. This idea also works out. And so you see, of course, this is a simple cyst algebra. So to make I mean, the cyst algebra, the example I give is not simple, but this is simple. But even for this cyst algebra, the exact same idea would work out. Okay, and so this illustrates the power. Although the method is very elementary, but you can. So the way it works is exactly similar. You cut the circle into like union of some very small, tiny intervals. But it depends on, so this decomposition depends on the R. So that's why this method only works at certain scale, not like it would not work if we just try to go through this process for the general cyst algebra. Yeah, but anyway, this is quite, it can work quite generally. So I will just say a few words how to make this work. For example, like this cross product, and if you have so-called finite asymptotic dimension in sense of Gromov, then you can make the computation work. And so here is the concept of asymptotic dimension. It's just an analog, like larger scale analog of covariant dimension. Okay, so yeah, so this method has some teeth. Now, in general, like if you have a cross product on a compact space, like a group G acts on like the space by homomorphism, and then like for example, like Z acts on the circle by irrational rotation, and so there is a concept introduced in my work with Eric Gentner and Rufus Willard. It's called dynamic dimension. If it's finite, essentially this method would work slow. So this actually includes a lot of examples. Okay. Actually here, roughly, it's the concept. Maybe I just say it in a different way. So if I have an action on compact space, of course, you have a groupoid, right? You have a groupoid. Now, in the direction of G, the group G, if you given finitely many elements, E, okay, then you can always cut the space X into finitely many pieces. Actually, each of the pieces normally is a disjoint union of many small intervals, not the intervals, small open subset. Okay. Now on each, if you restrict this groupoid, this finitely many elements to this groupoid, if you let it generate a subgroupoid, it will be finite in the direction of group. So you cannot go very far. Okay, so that's essentially the concept. I'm just describing it in a different language, probably more intuitive. So this is a little bit more formal. Yeah. So it's very natural, but it's kind of surprising. This, for many natural examples, this the so-called dynamic dimension is finite. Therefore, you can use this technology to compute the KCL. Yeah. So this is called, yeah, dynamic asymptotic.
Can I ask you,
yeah,
because it has some resemblance to the Rocklin dimension, is there any relation?
You are right. You are right. So we, I think we developed all those things for purpose of computing K-theory, but then I guess people from dynamics and system algebras introduced different concept. There are some relations. So people wrote papers about this later on. And I think essentially one can estimate one from each other. They are different. They are not the same. Yeah, yeah, you're right. You're right. That's it. Yeah, yeah.
Okay, that's good because we introduced a bunch of other dimensions of actions of compact quantum groups on unital system algebras, where some versions of local triviality dimensions. Classically, they are all just Schwartz index, if you want. And this is all very subtle. And we ourselves have 3 variations, and the Rocklin dimension is the 4th one. And now we are telling us about the 5th one. So there is an incredible diversity of dimensions for group actions on sister algebras.
Yeah. So this one, so I should say we are like ignoring the dimension of X. Yeah. So in estimating your dimension, you probably should have to add back the dimension of
X. Mm-hmm.
X. So, but in any case, yeah. So yeah, well, it's a very natural concept. I'm glad it's related to what you guys are doing, and yeah. But we so we introduced this concept for the purpose of computing K-theory. So yeah. Yes. So I should mention that later on, like for example, Clementon, Lofers generalized this concept to Fourierian, in the context of Allen's index theory for Fourierian. They wanted to compute the K-theory of Allen's Fourierited algebra. So yeah. Okay, just if you take, this is a little bit crazy, but if you take the Stonechek compactification with a huge space, then this concept is basically the same as Gromov's asymptotic dimension. For example, if you look at this group, that it acts on the Stonechek compactification, then it has finite asymptotic dimension. Well, I guess, well, I mean, this space is kind of bad, but from this point of view, it's easy to understand. Okay, so now Avi and I wanted to generalize this concept to general, like, geometric system algebras, trying to make sense out of, like, what is an asymptotic ideals. So I guess, so we, so if we have a geometric system algebra with a length function, and this is what we call neighborhood, like our neighborhood, you just multiply whatever subset you have, you kind of multiply by elements with length R to see what you get. So this is supposed to be a substitute for ideal. Okay. Now, of course, this is not a condition. You don't. So this is the concept of asymptotic ideal. So actually, is very flexible. But with that, actually, we can now define the concept of system algebra with finite asymptotic dimension. You can decompose, like in each scale, you can decompose to like a number of pieces, and each of the piece like is something nice. I don't want to define what this is, like something you can understand. You can compute the case here. Okay, that's what it is. So then you have you have this Mann-Vittori sequence. And so under this condition, you can actually, for example, prove the Conus formula simply by computing the KCL in one of the variables. So this is something we and I did a couple of years ago. Okay, so yeah. So now I'm going to talk about something more recent, something I have been working with Rufus. Well, actually, we have been working with each other on this for more than 10 years, but we were always busy with something else, so we never kind of loaded it up. But finally, well, I guess that's one good thing about the pandemic. When we stay home, what else can we do? And I said to Rufus, now probably it's a good time to write this down. So we meet with each other for every week. Over Zoom. Eventually, we wrote this down. Okay, so let me just introduce a basic concept. Well, basically the concept of decomposable algebra. I mean, the basic idea is the same. You try to decompose the system algebra into like some pieces in that way you can deal with. Okay, so but let me just set up the notation to say like, well, this works for any metric space. Well, in our case, they will be subset of system algebra. Okay, so if like one subset is epsilon contained in another subset, if this is, I guess, well, maybe we just draw a picture, if this is x, this is x, and y is like very close. Well, maybe I draw, well, yeah, draw it. Let me draw it in a yellow color. Like it's very close, like. Okay, so we say it's decomposable if for every finite, because for K-theory, we are only interested in, finite subset, right? And for every epsilon, we can cut this subset into something which are basically finite dimensional. Okay, that's the idea. So this H is the partitioning function in some sense, this H, okay? This positive contraction in A. And this H like almost commute like with everything in X, and it will cut. If you multiply this will be epsilon contained in some finite dimensional one, and the other part is also epsilon contained in another finite dimensional algebra. Now, this sounds like a condition, but actually this is not much a condition. And you can prove for what we are interested in, it's always satisfied. Okay, so condition 1 and 2 are almost free, but it's condition 3. Condition 3 is the tricky one. Essentially, we want to say the intersection also is like almost contained in a finite dimensional algebra, okay? Now, this concept, if you look at it in the context of what I talked about before, it's essentially a concept of like, it's a dimension 1 concept. It's dimension 1. You can chop things into something 0 dimensional. So this is like asymptotically being decomposable just means that it's a dimension 1 condition, okay? Very, very intuitive, okay? All right, so this is our crucial concept, okay? All right. Okay, so now using this
Sorry, Guoliang, would you give some examples for this definition?
Oh, so I guess there are lots of examples, but I have to use like, it's like more like a dynamic, well, essentially the example I had, it's, okay, so let's look at the example I gave here. The circle.
Okay.
where this one, okay.
Yeah, perfect.
So the circle, you see, I'm even the one before.
Mm-hmm.
And so I'm cutting, like, essentially I'm cutting into two pieces, right?
Mm-hmm.
So what is the H? The H is essentially the partition of unity. You see, I have two functions, cutting the whole thing into two pieces, right?
Mm-hmm.
So I have a partition of unity function, okay? One is H, the other you can use 1 or minus H,
Mm-hmm.
okay? So that's it. So in this case, you can also do something similar, okay? But you just cut S1 into two pieces, okay? So the function is the partition of unity is really a function inside, like it's a continuous function on the circle.
Yeah.
Okay.
And it's a positive contraction.
It's a positive, yeah. It's a partition of unity. Yeah. So sorry. So it's very natural. I mean, this is like, yeah, it's maybe it's a partition of unity. Okay. So this is like a dimension 1 condition. Okay. Now, actually, in system algebra theory, dimension 1 is a generic phenomenon. That's why we are concentrating on like dimension 1. Okay. All right.
Thank you.
So, and using this kind of quantitative ideas, Rufus and I can prove that if it's decomposable and with like K series, trivial K series, and it satisfies UCT. Now, you might say this is a serious condition. This is not, because according to Kirchberg, and it's enough to consider trivial K series things. Okay. Now, it turns out, so by a theorem of Kirchberg, to prove the UCT, universal coefficient theorem, for all nuclear system algebra, it's equivalent to like so-called Kirchberg algebra with 0 K series. It's decomposable in our sense. So the condition we give sounds very special, but you know, just for the so-called UCT. Now, of course, the UCT, the reason we are interested in UCT is, you know, it plays like a central role in recent progress in George's classification project, and you need the UCT to. Okay, so by work of Kirchberg, the UCT for nuclear system algebra actually is equivalent to proving the unital or unital Kirchberg algebra with trivial K series is decomposable. Okay, that's a consequence of this theorem, and also a theorem of Kirchberg, essentially. Okay, so
may I ask a quick question? So
yeah, sure.
So I wanted to ask about the relation between decomposability and nuclearity.
Oh, that's I think no. In general, nuclear system algebra are not decomposable. It's
So,
only yeah.
But in your theorem, there is no nuclearity assumption.
Oh, our condition will imply nuclearity.
Okay. Okay. Thank you.
Yeah, but nuclearity does not imply our condition. So yeah. Okay, so I guess should mention a system algebra is called Kirchberg algebra if it's separable, simple, like purely nuclear, purely infinite. So okay, so now let me discuss some of the concept which goes into the proof. Rufus and I wrote 2 papers, but the application to UCT is in the second paper. So they are all, we just put it on archive maybe, is that 2 weeks ago, 3 weeks ago? Yeah, so everything is on archive. Okay, so the main thing to prove this is to introduce like a theory of quantitative K-homology or KK theory, or sometimes we call it controlled KK. Okay. Okay, so here is the concept of quantitative K-homology. I want to say it's very elementary. It's actually okay. So instead of like using the language of geometric system algebra, I now just choose a subset. Could be well, you can imagine it's a finite subset. Okay, and because for K-theory purpose, we are only want to like understand a finite subset. Okay, so I'm going to define like a quantitative K-homology for a finite subset. Okay, so it's not, X is not even an algebra. So A is a system algebra. Okay, so it's represented by a pair of quasi-projections. Well, that's just, K is just the algebra of compact operators. So, I mean, with a unit adjoint. So essentially, what we need are just a pair of projections. I mean, in the unitized compact operators, but how are they related to X? Here, that's the key condition is we want them to almost commute. Okay, but of course,
is that related to like to the Paschke dual?
Oh yeah, that's very much so. I will explain the motivation. Yeah, you're right, Alan. Yeah, it's very much related to Paschke duality. Yeah, and so then if I like, of course, after taking the homomorphism to C, we want this pair to be the same. So that's the only thing. Okay. So this epsilon is an epsilon control. So this is the quantitative K-homology. So it's basically represented by something almost compact. So a pair of like quasi-projections which are compact operators. Okay, so just to explain Alan's point, so why is this like a natural? How is this motivated? This definition, and here. So let's look at the case. You have a compact smooth manifold. You have a Dirac operator. Of course, then we have, it's Fredholm. It's we can study its index theory, but you can represent its index. Especially in the heat kernel approach to like index theory, you can represent the index by a projection with very small propagation. So by kernel operate, which are almost concentrated on the diagonal, right? So with very small propagation. Well, actually, basically one projection is enough. Okay. And if you have like a kernel operator, if you have a kernel operator like KXY, like this kind of operator acting, say, on a function Fy, so if K is like the support of K is like almost on a diagonal, like almost like concentrate almost on a diagonal, then of course it almost commute with multiplication of continuous functions, right? It's almost commute. So that's so in this case, and actually this represent like the K-homology. This, okay. So a K-homology element can be represented by like just finite matrices with small propagation. Like it can be computerized in a way, K-homology. finite matrices are something we know how to deal with. Yeah. And so that's the essence of this definition. Like when you have like in the space case, yeah, you just want to represent K-homology by essentially finite matrices. Okay, but with the condition that the propagation is very small. Okay, and that's essentially this general that motivates this general definition. Okay, now of course you can similarly define K1. Okay. All right. So now how is this related to general K-homology of a system algebra? So you can just, if you wish, you just take an increasing sequence. Well, if you would like, even just finite subset, and so that the union is dense.
Excuse me, may I ask a question?
Yeah, sure.
Since you have assumed that the set X is contained in the unit ball of A, so how it could happen that the sum is dense in all of A?
Oh, good point. Good point. It's more, I should say,
in the unit ball, yes.
Yeah, the unit ball. Yeah. Okay.
Thank you.
Yeah, unit ball. Good point. Like essentially, it will give you everything. Yeah. Okay. So how is this related to the usual K-homology? So there is this exact sequence. This is a lim1 exact sequence. There is a natural map to the inverse limit. But there is like a lim1 error. Now, if you just want to know how things are paired like with K-theory, then this term is good enough. But there is something like some kind of ghost kind of elements in the lim1. So that's how. So this quantitative K-homology is related to the usual K-homology in this way. But the good thing about those quantitative thing is, I think it's more like a local theory. So you can, when you try to compute things, you can only concentrate on the local part. And so this is a result saying that the global K-homology can be recovered from the local quantitative like K-homology in this way. Now, again, what is good? So using this sort of thing, how would we go to prove like the UCT? And essentially, let me just say, this condition allow us. This is like allow us to establish a Meyer-Vittori sequence for quantitative K-homology. This condition, this partition, the existence of such a partition of unity. Now, so you like you essentially reduce everything to like, to find something finite dimensional. Of course, we know things are true finite dimensional. Okay, so it's a very simple idea. Okay, so that's actually all I want to say about. I have to say, excuse me. I'm not an expert on like system algebra theory, so I think Rufus knows more than I do. But any like comments on our paper will be very much welcome. And also, there is a likelihood we missed something in the literature in the reference. So if that's the case, let us know. We would appreciate it.
I don't know who's making the noise. I'm trying to.
seminaret.
Okay, sorry.
Okay, yes,
Magnus,
I've got this Magnus. Okay.
Yeah.
Sorry, because I have to scroll through everybody to see who is unmuted.
Okay, so yeah, so these are all like connection to system algebra theory, which and if and now I want to like move to some other applications to like something I recently did with yeah, so with Zizang and Hao. Okay, so our motivation is trying to solve to study some of so Gromov proposed a lot of conjectures about scalar curvature in a more quantitative way. Okay, I'm not going to mention that. And so how Zizang and I established a connection between how big is a positive scalar curvature is and like vanishing of high index in like quantitative K theory. Okay, so if this theorem essentially says if the scalar curvature is pretty big, then it will vanish already in the quantitative K group in some scale. So the scale is like quantified. Okay, and this can already be used to prove like some version of some of the conjectures and of Gromov. So it's just a connection. So it's just a bridge between what we are doing and what Gromov wanted to do. Now I should mention actually Zizang. So in Zizang wrote a spectacular paper recently on archive. He went further. So this paper is on archive if you're interested. He used like this kind of operator K theory to prove quite several of Gromov's conjecture. I think it's a really spectacular piece of work. Okay, so this connection is interesting. So it's quite interesting. So Zizang solves several conjectures of Gromov. So I think he put his paper on archive about a month ago. So if you are interested, you can find his article. Yeah, really very beautiful work.
Excuse me, may I ask a question?
Yeah.
So the constant depends from the choice of what? Of M, of the Riemannian structure, of the spin structure, and
the constant is independent. So I should say this omega 0 is universal.
For given dimension, yes? Or
the dimension, yeah, maybe the dimension, but it's universal. It does not depend on the manifold or anything. But yeah.
Okay, thank you.
Yeah.
It's strong.
Yeah, it's a well, for me, what's interesting is, this quantitative K group, not only it's a tool to compute the usual K theory, it has some use. Okay, so, but well, of course, Zizang went ahead to solve. I mean, he does not. I mean, Gromov proposed a lot of questions, but I think he solved some of the, yeah, really nice conjectures. So, okay, so
and also it's really a constant, meaning it's a real number. It's not a function on a manifold like the scalar curvature.
Oh, this C is a constant. This C is a constant. Peter, is this your question?
Yeah, I mean, it's because a K is bigger or equal, greater or equal than C uniformly on M. So I thought that maybe C is a function on M.
Oh, no, K is a function.
Okay. Okay, well, so C is any constant function. Okay.
Yeah, K, yeah, C is a constant, K is a scalar curvature. Did I say K? Yeah, K is a scalar curvature. So K is a function.
Okay, good.
Yeah. Okay, so I just want to mention this. Now there's another application. I'm actually I'm quite I found this quite fascinating. Okay, so this joint work again, it's because of the pandemic. You know, Shimo, for some weeks, he sent me a lot of emails, and then we had some Zoom meeting. He was asking me, oh, you know, and he and Alex Lubotsky are very interested in this question, and he wants us to look into it. So okay, so I mean, I guess Shimo is the chair of the department, although he's very kind of busy, but he still has too much time at home, so we have to just do math together. But anyway, so we come together, and we realize what Shimo and Alex Lubotsky, what the questions they're asking is very much related to what we were doing. I mean, but you know, we were not thinking about this. So that's another good reason to work with people from the different areas. So here is a question. So he's interested, like when like so-called stability. Well, they use words like testability. Anyway, so there's some computer science aspect. So if you have like if you're given like a discrete group, and if you have a bunch of maps which are asymptotically, they are homomorphisms. I think asymptotic, for example, if you like in a homomorphism, if you like GH, you want to be exactly phi G phi H, but in this case, they are like going to 0 in norm, but not exactly 0. Okay, so that's what an asymptotic homomorphism is. Okay, the question is, can you make it like can you find a sequence of like exact homomorphisms which are very close by? So this subject, there's a lot of references. To my surprise, yeah, I think so. These are like probably one of the first group of people who
I think you mean Sorensen.
Soren. Oh, you're right. I did some cutting and pasting, and I think the yeah, it's like yeah.
And I think what you missed is a special character. It was
yeah, the special character was missing when I did cutting and pasting. Yeah, sorry about this. Yeah, so okay, so this now, so it turns out that these are related, very much related to quantitative K-homology. But actually, in order to attack this problem, we have to modify the quantitative K-homology we just introduced. Have to make it a little bit more special to fit with this like problem. But so here is one sample example we can do. For example, if it's like hyperbolic in the sense of Gromov, then G is essentially never so-called matricially stable. If the Baum-Kahn delocalized cohomology group is non-trivial. So it means that almost all the time it cannot be stable. I think that essentially, yeah. So generically, it will never be stable. So that's probably the kind of result. Oh, I should mention that the Baum-Kahn delocalized cohomology group contains the group cohomology. So if in addition it's residually finite, then there are some other technology, like for example, Maris Stadler proved that it's not maturely stable if the group cohomology is non-trivial. He used like quasi-diagonality and the Baum-Kahn conjecture. Of course, we know the Baum-Kahn for hyperbolic groups, but quasi-diagonality, that's hyperbolic groups are like, usually not quasi-diagonal. So also in general, we don't know if hyperbolic groups are residually finite. So our approach is more like constructive. We just use this quantitative K-Homology stuff. So I thought this is an interesting kind of connection, which like explains that, well, I guess other than computing K-Homology quantitative, this kind of quantitative K-Homology has, I found it's interesting. It has some other applications. Okay, so I think, although Peter said I can talk
90 minutes.
Yeah, but that's all I have. Yeah, thank you very much. I will be happy to answer questions.
Thank you so much. I'll be fine with clapping hand. Yes, very good, very good. This is a beautiful talk and a beautiful mathematics. Although I have to admit that if this is your concept of talk which is comprehensible to a general public, then I'm not sure I'd like to listen to your technical talk. Anyway,
yeah, I'm avoiding the technical part.
Yeah, but anyway, this is very, very nice. And now let's open the session of questions, and you can fire at will. So whoever has a question, please ask.
I'm sorry. So I guess I should say that I'm not an expert in a lot of things I'm talking about. So if I'm missing a reference, forgot to mention someone, in the article, write us emails. So like, for example, in this subject of stability, I only got interested because Shimo was send me so many emails and wanted to find this out. So I started to learn about it. But again, I'm sure we miss. When I try to learn the subject, I probably don't know all the references. And yeah.
Well, I will definitely alert Tatiana Schulman and Soren Ehlers to your work.
I should say for the last piece of paper work, we have not written it up. So, but hopefully in a few months. Yes. So so it's joint work with also my former student Jian Chao Wu and Shimo.
Okay, questions, please go ahead. Richard?
Oh, it's okay.
Okay, no questions. Alain, have you got any more questions? You are mute, yes, now.
Yeah. Okay. No, I mean, I think, it's an extremely interesting development, this development of the K-homology in this dual manner. What I was wondering about was, that it should be applicable also to operator systems, because I mean, in a way, what you are doing is the relation with the ambient Hilbert space, compact operators, and so on, and somehow, operator systems, because they are precisely embeddable in operators in Hilbert space. I mean, they should, and that's the issue of finding the proper definition of K-homology for these things is quite interesting, quite open.
Oh, yeah. And you have a very good suggestion. We have not thought in that direction, but that's a very good advice. Yes.
What I have in mind, for instance, is the fact that when you try to approximate, I mean, from the physics side, when you try to write down the higher Heisenberg relations, when you try to write them in a finite manner, when you approximate by a finite dimensional stuff, then I mean, this type of approach to the K-homology should be quite relevant, really. I mean, I presume that you can do that whenever you have a spectral triple. You can take functions of the Dirac operator and you have exactly what you need to localize as you're doing.
Yeah. So yeah, I think Ella made an excellent point. For example, like in this finite manner, like for example, for the circle, like of course we understand it very well. D is like I, D, theta, but in this finite way, what it is we can just discretize the circle like this. Then you just shift in one position. But you need to, for their distance, because it depends on the epsilon, and you need to make them like very close by, like more and more. But on the other hand, I wanted to make this work for S2, like for the Dirac operator. Can we write down like a concrete matrix representing like a finite matrix representing the K-homology? We know there is one, but I don't know how to write down one. So,
well, maybe quantum groups could be useful. I don't know. I mean, the quantum sphere and quantum groups could be useful. I have no idea, but
well, this kind of discretization, right?
Yeah,
it's kind of discretization. Yep. So this is quite interesting. It's also I feel like it's related to like trying to define what is scalar curvature for like a discrete space. The two questions should be somehow related, I think.
Yes.
Actually, once again, what was your statement that if you have a Kirchberg algebra with trivial K theory,
it's decomposable. So
then it is UCT.
Yeah, that's equivalent to
the standard one. No, if you let different. So you mean it? Oh, yeah, because the composable ones satisfy UCT. Okay.
Yes.
Okay, then it follows. Yes. Okay.
Yeah. Then it follows. Okay. Yes.
Yep.
Yeah, but the key idea behind it is all K-homology, they can be represented by things as simple as that.
Yes. Very simple. So it's a kind of finite. Yeah. Finite approximations. Yes.
Yeah. Can be discretized, so to speak. But fine. So if we want to make it computable, like something the computer can deal with it, then somehow, we like.
The KK class is computable, finitely computable, then yes.
Yeah, exactly. Yeah.
Okay. Anybody else?
Okay, so maybe I again will ask, do you need to approximate really the space or some approximation of the algebra of functions on S2?
No, we don't need to approximate functions.
You don't want to discrete? Okay.
So see, like for example, for the case of circle, if you just take a finitely many like functions, you can always you discretize in such a way that it almost commute with the multiplication. And so the pairing of this K-homology element with K theory is also very easy. You just multiply like pointwise. So then with this discretized K-homology element, you get a finite matrix. Essentially, the rank of this finite matrix is the pairing. So you can read off pairing very easily as well.
The next another question, sorry. So if you have this kind of finitely, so kind of controlled theory, a gamma element will be identity, right? Say group acting and group which kind of preserves this kind of filtration. If the group action preserves this kind of filtration, then assembly map would be an isomorphism.
Yeah, I mean.
Or what? I'm asking. I don't know. But
so I have So I think at some point, Rufus and I were trying to discretize the things like the gamma element. So I think, I think it's Zhang and I were doing this for another purpose. So the gamma element, you have like, like a very nice like Fredholm operator with index 1. So if you can discretize that, and Zhang and I at some point tried very hard because we wanted to prove some of those fellow Jones like algebraic K-theory stuff. If you can discretize this, then you can adapt some of the technology we have to the algebraic world. Mm-hmm. Because what's missing, like comparing our approach to their approach, they don't have anything like that. So, but in their world, you need to be discretized,
yeah. Mm-hmm.
That's another motivation, trying to discretize all those things.
No, but I was thinking slightly differently. So there is this Joachim's picture of the assembly map.
Yeah.
Kind, right? And and just that my feeling is that if you restrict it to this kind of if you've got your finite iteration of the algebra and the group, and you preserve, and the group action kind of is, let's say, it does not have to preserve filtration, but is kind of more uniform with respect to this filtration. Then the corresponding version of the assembly map kind of has good chance to be an isomorphism.
Yeah,
right?
I see.
It's not the original assembly map. It's restricted to this kind of controlled K-theory, controlled equivalent K-homology.
Yeah,
but it feels a bit like it can be there, right?
Yeah. So using this language, the assembly map, so maybe it's probably compatible with Johan's approach, but it can be described in a very simple way. Because this element, like, so say if this is on the classifying space, if you lift this to the universal cover, this is already in the K-theory of, it's already in the K-theory of the group system algebra. So assembly is like automatic in this case. But where do we use, like, you see, to lift it, you need a small propagation. If you have small propagation, you can lift it to the universal cover.
No, I mean something else. So there is this kind of universal construction of assembly map. So okay, Joachim is around, right? So he could say what it is himself. But so the idea was to think about universal C-star algebra generated by projection in a cross product. And then you can formulate, Joachim formulated assembly map kind of in these terms. So you looked at this universal C-star algebra and you translate it into the basically some kind of equivalent KK element. There's natural K element and you translate it somehow in equivalent KK element. And then there's this problem of, and then the problem is that neither one side or the other side of assembly map are kind of finitely generated. So you can see it on finite pieces. Now you're kind of, so your controlled K-theory, K-homology, I guess, as well, are things which can be seen on these finite pieces.
Yeah.
Right? So it's quite possible. So if you write down assembly map in these terms, then assembly map would be an isomorphism from controlled K-homology, equivalent controlled K-homology to equivalent K-theory of cross product.
Yeah.
So given some filtration, which is, I guess, kind of invariant or quasi-invariant under group action.
Yeah. Yeah, it sounds like there should be some connection. Also,
should be some kind of connection, right?
Yeah,
but do I understand what Guolang was saying correctly by saying that if these elements are sufficiently localized, because the groupoid of the original space is locally the same as the groupoid of the covering.
Yeah,
and you don't have any problem to lift. So
the
assembly map is sort of obvious in this way.
Yeah, exactly. So in this, the assembly is just like a lifting.
It's a local isomorphism of the two groupoids. Yes.
Yeah, exactly. Yeah, exactly. Yeah, exactly.
Okay. Anybody else?
I have a question.
Yeah, oh, sure.
Is this controlled version equipped with a kind of asymptotical functoriality?
Yes. So so if you have like homomorphism which respects like those lengths or asymptotically respect, then yes.
So what are conditions for these homomorphisms to preserve these conditions?
Which
are there some automatic assumptions?
So so let's see, if I have like two system algebra, right? Each with a length function, so you can give a filtration. Let's see if it exactly respects, then you have a little homomorphism.
Yes.
But if you need to sometimes make the R slightly bigger, then you have an asymptotic homomorphism. So you do you do have like functoriality, yes, in that sense.
What about a kind of quantitative Bott periodicity, Morita equivalences?
That's a good question. That's so for there is Bott periodicity. Bott periodicity, I think somewhere in one of my old paper with Avi, there is a proof, but the proof, I have to say, none of us like that. So like for example, for K-series for Bott periodicity, you have this very beautiful proof by, essentially by Atiyah and using linear algebra. But that proof you cannot adapt it to the quantitative setting, because that proof it only works in the category of idempotent. And so when you try to, so you lose like control on the filtration or the propagation. So so this is, I think someone was telling me he has some other ideas, but they have not written up. But if you have a good proof, it would be fantastic, because I mean it's an elementary problem, but I think my old proof with V use like elliptic operators. So I think you should not need to use that, because
I'm not sure if I understood Alain's question about cohomological side. Is there a quantitative partner for the turn character for this quantitative K-theory?
Oh, that's something I thought quite a bit. So Alain's theory, the conchain character relies exactly on things being like a projection or idempotent. But on the other hand, in one of the paper of Alain with Henry, and also later Michael Pushnicki, they developed something asymptotic cyclic cohomology theory that might fit better. So I at some point I thought about this, but but that's a very interesting question. So how to pair like Alain's cyclic cohomology theory with this kind of quantitative.
Okay, thank you very much.
Sure.
Anybody else, please?
I would like to ask, could we go back to this slide where we had the exact sequence of the quantitative K-homology? Okay, this one.
Yeah.
Oh, yes, yes. So here xn are arbitrary sets. So
yeah.
I'm pretty much puzzled. What is the geometric interpretation of this possibility of taking just arbitrary sets, not necessarily algebras?
Oh, okay. So I think, so this is just, so yeah, let's think about like you are choosing like finite, say finite.
Okay, okay.
Oops. Finite subsets. Then, in nice situation, you can have those partition of unity thing and to decompose this to something nice. Then you use May-Vitelli sequence to compute them. So that's why we want to like focus on those like more like quantitative K-homology.
But I guess the spirit of the question was how do you even make sense out of K-homology for something which is not an algebra?
Oh,
yes. So this was defined. Okay, so
this was defined.
The definition was okay, but I'm puzzled with the fact that in this picture between correspondence between geometric object and algebraic object, arbitrary set corresponds to, I don't know, nothing.
No, let me just maybe explain from a more spiritual point of view. So K-homology, of course, one of the major purpose of K-homology is introduced to try to pair up with like a K-series element, right?
Okay.
Now, a K-series element, whatever you need to deal with, it only lives like in a finite set, even if you try to prove like one is equivalent to another, this always can be implemented in a finite set, subset. Okay, so what I'm saying is that in terms of pairing, as far as pairing is concerned, all you need to do is to worry about finite subsets.
Okay. So
I mean, you don't need to deal with it's like a finite. What is a finite set? It's like a multiplication table essentially. It's like that's what you need to deal with, like groups. You just big multiplication table.
Okay, so we don't care what is xn in terms of algebraic picture, but we do care.
We don't really care. So it's kind of
xn, yes.
It's kind of disturbing, for us algebraists to consider something which is a subset, but it's okay.
Okay, so sorry for this naive question.
No, that's a good point. I guess we somehow it's okay to get away from algebras. So.
And maybe just one more question about this matricial stability, your last slide.
Yeah.
So I don't have any intuition about what does it mean, this condition. So this is in some sense this is a wild condition or somehow tame.
I think this is something the group people, algebra people have been studying. Something which is this has a long history. I think this kind of subject, something which is almost something, is that exactly something. So it's so this is like it's almost an isomorphism. Is it close to an exact? I mean, it's almost a homomorphism. Is this close to something which is like which is an exact homomorphism?
Okay. So I'm fine with this, but I don't have any intuition. If you give me a group, I couldn't guess.
Yeah, but take a group which is not linear at all, which has no non-trivial homomorphism to matrices, But then you can easily imagine that you have almost homomorphisms.
Yeah.
Okay.
So
this is a wild condition, yes.
Yeah. So for example, you could ask: is every hyperbolic group residually finite? For group theory people, that's a long-standing open question. In essence, this theorem says, in K-theoretical sense, the answer is yes. You can find a lot of like almost ones, which gives you a lot of non-trivial cohomology. Yeah. So,
okay, so this
so
is also the part
yeah.
of the last theorem, yes, to somehow to be able to claim whether some group is matricially stable. Yes, this is the purpose of the last theorem. Yes.
Yeah. Yeah.
Okay. Okay. Okay.
Yes.
Thank you. Thank you.
Sure.
Anybody else? I don't see any.
Yeah. Okay. Maybe one more. So, yeah.
Okay. So, sure. Listen.
So you have it. What about controlled version of KK?
Oh, yeah. In our article,
you said something
about
bot periodicity, right? So
yeah. So in so in our articles with Rufus, it is controlled version of KK. So I'm just.
So that has to, but doesn't that contain proof of bot periodicity?
Oh, bot periodicity
by itself, for control version.
Yeah, about the periodicity. Yeah, I think we did not deal with that. So, but I think the same argument with V works, but it's not. So as I mentioned, it's not a proof we liked.
Well, you need controlled version of Dirac for R2, right? Or for R.
It's just adapting in a way, just adapting Attia's proof. You know, Attia has more than one proof. The proof he liked, like he used a little bit Dirac operator. Yeah.
No, but we're talking basically we're talking about kind of asymptotic homomorphism proof, right?
Asymptotic
so kind of
one
asymptotic.
has to be very kind of it's a very subtle issue, like especially for the stability issue. You know, for example, in Alan and Nigel's theory of asymptotic homomorphism, you need to do suspension. And but here, like to deal with this kind of question, like stability question, once you introduce stability, like suspensions, then things like breaks down. So what I'm saying is, like, we really want to do this in a discretized fashion without even doing suspension.
No, but in some sense, what you want to do is to give yourself some kind of controlled version of Heisenberg group extension, right?
Controlled version of Heisenberg.
Because that's this. Well, that's what periodicity is.
Yes.
In one other way.
Yeah.
So you want controlled version of that one.
Yeah, you mean what you mean is that the deformation of the Heisenberg group, huh? Exactly, yes. To the
precisely, right?
Exactly.
Okay.
Yeah, deformation might be even better actually, because you might, for a small value of the parameter, control as much as you want what happens.
Okay, deformation. But can one do this kind of deformation in a discrete way?
You probably don't need it, I think. Yes.
Oh, okay.
It's not a question of discrete. You need some kind of kind of filtration that you control, right?
Yeah. No, I think it's a good idea to use the deformation. Yes.
And then you have your filtration on compacts by, well, standard, just pick up an increasing sequence of financial projections.
Yeah.
That would be your one filtration, right?
Yeah.
And then your approximate representation of R2 function on R2.
Yes.
Well, asymptotically works, right?
Yeah. Probably the Weil dequantization also. It's the same thing. Yes. Yeah.
Just a question. I don't know. Just a feeling, right?
A good question.
Yeah, so letting H bar go to 0 in the Weil quantization. Yes. Yeah. That's a very good point.
All right. Anybody else, please?
Maybe just one more, if I can.
All right. Yeah, surely.
So is there also an adaptation of this theory to von Neumann algebras, or we are not interested in? K1 for Neumann algebras is always 0, but
no, but it's this measure theory. So
yeah, for Neumann algebra, yeah, we kind of lose the topology, as Alan is saying. Yeah.
Okay, thank you.
All right, it's been a very long session of questions. If you don't mind, Guoliang, I have just some extremely naive questions. I apologize in advance.
Go ahead, Peter.
I'm wondering about the class of your decomposable sister algebras. So you said that decomposability implies nuclearity, for instance, right?
Yeah.
And could you give us like a big class of decomposable sister algebras? For instance, I don't know, is every graph sister algebra decomposable?
It's so this is like so it turns out like in the world of like for nuclear sister algebras for in the classification project, essentially like dimension 1 is a generic phenomena. I mean, in general, decomposability is a strong condition. So, but for the UCT purpose, it turns out it's not, and it's been reduced to dimension 1 kind of algebra. So also there are theorem like among simple. So I think George is here. George probably can tell us more. Like for the kind of like there are theorem by Wilhelm Winter and his collaborators, and so in the world of algebra, they want to classify sister algebra generically dimension 1. So, I mean, of course, their dimension is different from our dimension. So that's also quite interesting thing, trying to relate these two concepts of dimension 1. Yeah, for example, like the Johann's algebra, it's a Kunz algebra, is decomposable. Yeah. So they, yeah, in our article, we give quite some concrete examples.
And I was also wondering, it's again a very naive question, but you emphasized it very strongly, and I think this is a very important relation, that having a length function on a discrete group gives you automatically what you mean by length on a sister algebra. Yeah, when you take this then convolution sister algebra of a discrete group. So now, forgive me my obsession with graphs, but if you study graph sister algebras, then you look at the space of paths, finite paths, and the length of a path is a very important number that appears. And somehow is this length of a path can have any relationship with defining a nice natural length function on a graph sister algebra?
Oh yeah, I think so. I mean, the concept like the word length on a group, it came from the path metric on its calligraph. So I mean, the way you are describing well, in that case, it seemed to be the exact the length, the same length. Yeah.
Okay, good. I think it's time to thank Guoliang again. So we're clapping hands. Yes, here they are. Thank you so much. The length function applied to the discussion was a big number, which means it was a very successful story. Thank you very much again. Thank you everybody for participating. And I hope to see you all in a week at the talk of Lara Mantini.
See you next week.
I stop recording. Thank you so much. See you next week.
Thank you. Thank you.
Bye-bye.
Nice to see you guys. Yes.